In this video, I'm going to discuss acids and bases. This is something when I started this playlist, I figured that people already knew about it, or at least knew about all of the stuff that I'm going to talk about in this video. But from tutoring students, so I have a new job tutoring students right now, and it's organic chemistry that I'm mostly tutoring. I found that a lot of them are having trouble with acid and base stuff, and so I thought I would talk about that. This is actually from chapter 2 in the organic chemistry textbook by L.G. Wade that I'm using. Well, it might be chapter 1. I'm not looking at it right now. But the point is, I started at chapter 3. And so this is actually kind of going back to something I figured people already knew. So if you're already familiar with acids and bases and pKa and pKb and the reasons why an acid is stronger than another acid or a base is stronger than another base and things like that, then this you could probably skip this video, but even then I might encourage you to watch this just to have a little refresher. I also encourage you to check out my acid and base videos, particularly in my inorganic chemistry playlist. So there is more that I have on acids and bases. But anyway, without further ado, let's get into this. First I'll discuss the Bronsted-Lowry acids and base chemistry here. And then we will get a little bit into Lewis acids and bases at the end. And so an acid is something in the Bronsted-Lowry acid and base theory. An acid is something that has a hydrogen that it can donate to something else to give it the hydrogen ion. So it's the H plus ion. It's essentially shuttling around H plus ions. And so, a hydrogen just has a single proton. And so you'll also hear people call it protons. Uh, you might hear things like deprotonation and protonate. And so those all kind of mean the same thing. So it's shuttling around these protons between things. And so this is sort of the canonical Bronsted-Lowry acid and base reaction. So this is the acid reaction. So our strong acid. So this A is being generic. It could be something like chloride in hydrochloric acid, or it could be a sulfate in sulfuric acid, or things like that. And so that A is just a generic acid there. And you put it in water, in a water solvent, and you will generate these H3O plus these hydronium ions and our conjugate base. And so that's the thing to notice here is we have the acid and the conjugate base. And of course, in this context, and that's an important point, is that it's very context dependent. This H2O is acting as a base, and this is its conjugate acid. And so one thing I noticed that my students that I tutor seem to be confused about is, so we call this the conjugate base, but we just call it the conjugate base in this context, because down here that same thing could just be a base. And so when we are talking about this reaction, we are talking about it in terms of the acid that's in the reactants and the conjugate base that's in the products. If we flip this equation around, because we can do that because of equilibrium and Le Chatelier's principle, if instead we wanted to look at it going this way, then this would be the base and this would be the conjugate acid. So calling something the conjugate acid of, or a conjugate base of something is very context dependent. And so don't get too caught up on, what does it mean that this base is a conjugate base and this base is just a base. It's more just talking about it in terms of reactants and products, really, is what it comes down to. The acid or the base is that which is here in the reactants, and then the conjugates are that which are in the products. But anyway, so what we have going on here is the water acting as a base is taking that hydrogen off of there, and so we end up with the hydronium, the H3O plus here, then the conjugate base, which is just the A after the molecule that has now lost that hydrogen. Then the canonical base reaction, so we have this A here, which is now acting as our base. The water is now acting as our acid. So once again, context dependent. It's all context dependent. So the water is acting as the acid. And so the base is taking a hydrogen off of the water here. And so the water becomes the hydroxide ion. And so this is the water's conjugate base here, and this is our conjugate acid from the A right here, from this base right here. And so if we look at the equilibrium expression for that, because this is Bronsted-Lowry acids and bases, we give them a special sort of thing here rather than just like K sub C or K sub EQ or something like that. Those are both kind of used interchangeably in equilibrium. This gets Ka because we're talking about acids, and this gets Kb because we're talking about bases. And so we see here, I mean, we could put the water in, but because it's a liquid, we usually don't count that. So we could put the H2O in here because that is one of the reactants, but this always just goes to 1 when it's a liquid. And so we can just kind of omit that. And so we have the H3O plus and A minus here in the top and the HA on the bottom. And so the stronger the acid is, the more it's going to go to products, the more it's going to shift or move in this direction or react in that direction. So our numerator here will get larger, our denominator here will get smaller, and this Ka will become large. And then with the Kb, it's the other way around. So we have the OH here in the numerator, and then our base here in the denominator. And so the stronger the base is, the more it's going to start taking hydrogen ions off of stuff. And so the numerator gets larger, the denominator gets smaller, and so the Kb gets larger. And so Ka and Kb can be used as a measure for how strong an acid is or how strong a base is. Then, of course, we have this here where if we multiply both of these together, because they are sort of inverses of each other, they will always come out equal to 10 to the negative 14, at least if we're talking about acids and bases in water. So the solvent dependence on this is important too. And if you check out my inorganic chemistry playlist, I do have a video on using solvents other than water in acid-base chemistry. So if you're interested in that, you can go check that out. But right now we're just talking about in water. So we see that we get some things canceling out, and so we get this right here. And so you'll often see the equilibrium expression for water as Kw, which is what we usually call this. So this is Kw being equal to our H3O plus times our OH minus concentrations. And so that's where that comes from. And of course, and I've done this in other videos, you can take these things and come up with the Henderson-Hasselbalch equation, which I'm not really going to talk about in this video. All right, so again, we have our Ka here expression and our Kb expression here, and I said those can be used as a measure of the strength of an acid or the strength of a base. But what you will see more often is you take the negative logarithm of these, and so that gives you the pKa and the pKb. So that p is telling you that we've taken the negative logarithm. So you're just putting a p in front of there. So pKa, and so that is used to measure or to describe the strength of an acid and the strength of a base. And so just like Ka times Kb is equal to 10 to the negative 14. If you then took the negative log of of both sides of this equation here, you would end up with this right here. So the pKa plus pKb is always going to be equal to 14. Again, talking about when we're in a water solvent here. And so you'll find charts like these. This is the one that's used in the book I'm using, but you'll find charts like these. They're kind of a dime a dozen that show the strength of acids and bases here. And so we see that we have the pKa over here and the Ka right here. And so that we also see here, this is giving us the acid and the conjugate base here, where for HCl, the HCl is the acid. We put it in water, it becomes H3O plus, and we get the chloride ion as our conjugate base there. And so we see this has a pKa of -7. Then we can go all the way down to methane here. And so I've talked about in previous videos how the methane hydrogens are considered to be not acidic at all. And so we can actually see that here numerically. So this has 50 here. And I guess I should point out too that because we are taking this negative log, what ends up happening is that the smaller the number, and pKa is the one that's used most often. So pKb does get used. pKa is kind of the one that you'll see most often. So as this goes down, that means the strength of the acid is going up. So these lower numbers, especially when we get into the negatives here, mean that it's a stronger acid, where something that's very positive, a very positive number here, is going to be an extremely weak acid. So a pKa of 50 is essentially like almost not an acid at all. You'd have to have an extremely strong base to deprotonate that. So yeah, this is kind of what I was saying above. So the acid here, if the pKa is low, then it's a strong acid. And so we get pKa going low, but that would also mean pKb is going high, because remember these two things, the pKa plus pKb is always equal to 14. And so the pKb is going to be equal to 14 minus pKa. And so they are opposites of each other like that. And so as pKa goes lower, the acid gets stronger, and pKb will get higher. And the opposite, or the inverse, is true of bases. And that this is going to be a theme in acids and bases, that the acidity of something and the basicity or alkalinity of something are always going to be inverse. And so you can actually see that with the equation. So our Ka times Kb being equal to 10 to the negative 14, that's supposed to be a 14 there, means that Ka is proportional to, well, it's equal to 10 to the negative 14 over Kb. And so it's actually equal to that. And so it's proportional to 1 over 1 over Kb. And similarly with the pKa and pKb, we see that because this is negative and this is positive here, that these things are inversely proportional. And so that's always the thing to keep in your mind when thinking about acids and bases, is that if something is a strong acid, then it's going to be a weak base, or its conjugate base will be a weak base. If something is a strong base, then its conjugate acid is going to be a weak acid. So that is probably one of the, if you take two things away from this video, that's probably one of them. And the other one is that the acidity and basicity of something is context dependent. And this can be discerned by the relative pKa. So for instance, we have three things here. So we have ethanol as a pKa of 15.9, acetic acid, which is at 4.74, and hydrochloric acid, which is at -7. So if you put ethanol into acetic acid, the acetic acid acts as the acid. But if you put hydrochloric acid into acetic acid, then the acetic acid will act as the base, because the hydrochloric acid is so much stronger than the acetic acid. And so the acetic acid in this case, it depends what you're putting it into. If you're putting it into an ethanol solution, then it's going to be the acid. If you're putting it into a hydrochloric acid solution, then it's going to act more like a base. And so it's, like I said, it's very dependent on the context here. All right, so on charts, the pKa is for the acid and the pKb is for the conjugate base. And so what I mean by that is we go up here, we have up here, this is the pKa for hydrochloric acid here, and that is for the HCl, and so that is for the actual H bound to a Cl. Now, if we get the pKb, which is going to be 14 minus -7, so that will be 21. That pKb is for Cl minus, and so it's for the conjugate base of it. And so, because what we're interested in with this pKa, pKb here is this hydrogen right here. And so whether this hydrogen is coming off of the chloride or being bound to the chloride. And so these pKa and pKbs are for the acid and conjugate base, or for the base and conjugate acid. Yeah, and so even in a protonated form, so there's that word that you'll see quite often, protonated. So something like acetic acid can act as a base in the presence of an even stronger acid, which is what I was talking about up there. And so that looks like this. So the pKb of our acetic acid is 19 here. And what I mean by that isn't the pKb of the conjugate base. I'm talking about the pKb of this oxygen right here. And so I guess that's another thing to think about with acids and bases, is this oxygen has a basicity, and so does this oxygen. And so a molecule can have multiple base sites, multiple acid sites. It could have base sites and an acid site. I mean, if you know your biochemistry, you'll know that there are amino acids, so that have a form that looks like this. And so this has this acetic acid, or this carboxylic acid here, but it also has this amine group. And so this is a base and this is an acid. And so these molecules can have multiple of these groups on the same molecule. And so what we are looking for is actually the acidity and basicity of certain atoms on the molecule. And so for this one, the pKb of this oxygen right here is going to be 19. So if we wanted to get the pKb of this oxygen right here, at least the pKb of that when it is deprotonated, then we'd have to do 14 minus our 4.74, which is what we already got up here. So that was 9.26. And so the conjugate base of this is a stronger base, and so that's why this oxygen here will get protonated before this oxygen right here. And I wanted to, well, I'll get to that here in a few minutes. We'll talk about this for now. So we're talking about the basicity of this oxygen right here. And so there are lone pairs on it. It's going to go take that hydrogen, that's going to go there, and we end up with this right here, which is going to have a pKa of -5. And so we see that this is a really acidic group right here. It wants to lose that hydrogen pretty bad, and so that's why you need something that's even stronger of an acid here, like the HCl, in order to protonate that right there, this oxygen right here. And so, yeah, the take-home message from this little part here, is just that there can be multiple sites that are acting as bases and acids on a molecule, and that if one of them is like a really weak base, so this pKb is 19, so that's quite weak as a base, you need a fairly strong acid right here in order to actually protonate it, in order for it to act as a base. And so that comes back to that context dependence thing. So if you put something in here that has a pKa that is sort of higher than 5, so if you put something in that has a pKa of like -4, -3, or anything above that, then you are probably not going to be protonating that oxygen right there. And so again, that comes back to that context dependence. That is, one of the sort of two take-home messages from this video. And so this is just kind of summarizing what we've been talking about. So the stronger the acid, the weaker the conjugate base, or if we want to put that in terms of pKa, the lower the pKa, remember lower pKa means stronger acid. So the lower the pKa of the acid, the higher the pKb of the conjugate base. Then the weaker the acid, the stronger the conjugate base. So the higher the pKa, so the weaker the acid, the higher the pKa. Those two things mean the same thing. Then the lower the pKb in the conjugate base. So lower pKb, stronger when it comes to bases. And so the stronger the base, the weaker the conjugate acid. So the lower the pKb of the base, the higher the pKa of the conjugate acid. And conversely, the weaker the base, the stronger the conjugate acid. And putting that in terms of pKb, the higher the pKb of the base, the lower the pKa of the conjugate acid. And so that is kind of the summary of what we've been talking about. And I think, this is one of those things that can be quite confusing with acid and base chemistries, all these inverse things. So how if you have a stronger acid, it's a weaker conjugate base, and things like that can get kind of muddled in the mind. But then you also have these pKa's where smaller numbers mean stronger, where, I think humans are kind of wired to think, oh, bigger number means, stronger. But in this case, and in a lot of acid-base type stuff, smaller numbers. So things like, with pH is the same, where a lower pH means a more acidic solution. And so pH, of course, is about the concentration of acid, where pKa is about the strength of an acid. And so that can kind of segue, I guess, into what determines the strength of an acid. And so the main thing probably is just this, the stability of the conjugate. This is probably the biggest thing here, but there are sort of 4 ways that I'm going to talk about here that can make the conjugate more stable. And so one of them is electronegativity. And so we see going from C to N to O to F, so carbon to nitrogen, oxygen to fluorine, the acidity gets stronger and stronger. And that's because this C is not going to hold onto a negative charge very well. And so this C is an extremely, extremely strong base, meaning that the H's on it are going to be extremely weak acids. We get to the nitrogen. This is going to be stronger than the carbon here, this acid here, but it's still going to be quite weak because this nitrogen isn't going to hold that negative charge very well. When we get here, the oxygen is going to hold the negative charge a little bit better than the nitrogen, so its conjugate base will be a little more stable, and so that makes it a little more acidic. Then when we get here, we now have the fluorine, which is going to hold on to the negative charge quite well. And so that's going to be a stronger acid. The conjugate base is going to be more stable, and so it's going to be more willing to let go of or release that hydrogen ion. And so, of course, basicity is the inverse of that. So as I said, this right here is going to be an extremely, extremely strong base. This is going to be a very, very strong base. This is I mean, this is like our canonical base when we're talking about acids and bases in water. And so technically, this when you have a solution of base, this is like the strongest base you can get. And I'm not going to go too much into that. I talk about that in my inorganic chemistry playlist, the acids and bases on there, but it has to do with the fact that when you put a base into water, as we saw before, so we have our base here plus our H2O. When you do that, it's going to become HA plus OH minus. And so even no matter how strong this is, when you put it in water, you end up with this as the base in water. And so that's why when we talk about sort of the strength of an acidic solution, we are interested in the pH, which is the concentration, because it's going to be the concentration of this here. So the concentration of that OH there, that's going to sort of determine the strength of the base of in a aqueous solution. But anyway, I don't want to get too much into that. Then we get to the fluorine here. This is going to be a fairly weak base right here. So I think hydrofluoric acid has a pKa of something like 3, and so this is going to be 14 minus 3, so it's going to have a pKb of 11. So that's going to be pretty weak as a base there. Another thing that determines this is atomic radius. And so, for instance, if we look at our hydrofluoric acid, like I said, as a pKa of 3, which is going to be weaker than the hydrochloric acid, which is a pKa of -7. We get to this hydrobromic acid, which is a pKa of -9. Then the hydroiodic acid, which is going to have a pKa of -10. And the reason for this is that that larger atoms are going to accommodate a negative charge better. So if we think about it like this, we have our fluorine here. This is an electron shell, and it contains these negative charges in it. Then we get to iodine, and it's this much larger shell, and it's going to have these negative charges in it. Well, negative charges are trying to repel each other. And so within the fluorine, they're getting much closer together, and so they're going to repel each other much more, where in our iodine, they can sort of stay further apart. So, this one can stay over here while this one stays over here, where on this one, this has to stay here while that stays right there. So they're much closer together, and so this is less stable. And so remember that sort of take-home message about what makes an acid or base stronger is it's the stability of the conjugate. And so the iodine, or the iodide rather, as a conjugate is much more stable than the fluoride as a conjugate. And so this is going to have a weaker acid. This is going to be a weaker acid than the hydroiodic acid. And so it's the atomic radius that helps to stabilize those conjugate bases on these acids here. But probably the biggest one here that's going to lend some stability is the resonance stabilization. And so I've talked about resonance in other videos before, but we can see here we have this ethyl alcohol here. It has no other, if we deprotonate this, if we take that hydrogen off and deprotonate it, this doesn't have, this right here doesn't have any other resonance forms, where if we deprotonate this one, we end up with this and a negative charge there, and that has this as a resonance form for it. And so we have another resonance form, and we can see just by adding this carbonyl oxygen here, we go from a pKa of 15.9 down to a pKa of 4.74. And so that's a significant increase in the strength of the acid for that. Then of course we have sulfuric acid here, which we see with these two carbonyl oxygens, one here and one here. We're going to end up with even more resonance structures if we remove a hydrogen from here, because it's going to be able to collapse down in here, and it could either go up there or down there, and so we end up with more resonance forms, and so that's why the pKa now drops to -10. And so resonance stabilization, stabilizing that conjugate base or conjugate acid, is going to increase the strength of the acid or base. And so this was the thing I said I was going to get to in a minute up above. And so this right here, remember up above I talked about how we could protonate this oxygen here if we are in a strong enough acidic solution. And so what I wanted to point out is that we are going to protonate that oxygen rather than this one. And so this right here is not going to be the way that it protonates. And so the reason for that is because this one has the resonance structure. And so we can have a resonance form here, so we can have electrons collapse down there. These ones go up there, and so we end up with this right here, and so we end up with that, and so now this one is carrying the positive charge, and so that's why this one is going to get the hydrogen on here, because this conjugate acid of that reaction of protonating that oxygen is going to be more stable because of this resonance stabilization. All right, so the other thing is the S character. And so we're talking about SP, SP2, and SP3. So the more S character, where we can put our 1 here and our 1 here. So this has 50% S, 1 here, 2 there. So this has about a 33% S. We put a 1 here, and so this has about a 25% S. And so more S character means stronger acid. The reason for this is that S orbitals have angular momentum. And the S orbital's angular momentum quantum number is 0. And so they have less angular momentum than other type of orbitals. So p orbitals have an L equal to 1, d orbitals have it equal to 2, and so on and so forth. And so S has the lowest angular momentum. Having less angular momentum makes electrons stay closer to the nucleus. And so you think of like angular momentum. So say we have something here, and it's sort of it has kind of a stretchy bungee right here with a weight on the end, and it starts swinging it around. The faster you swing it, the more it's going to stretch that out. And so when we have the lowest angular momentum, it's going to be the least stretched out on there. So it's going to be closer to the center. And so our electron is going to be closer to the nucleus. And being closer to the nucleus makes it more stable, because remember, the nucleus is positively charged, the electron is negatively charged. These things are attracted to each other, and so when we get them closer together, the sort of full system becomes more and more neutralized, and so more stable. And being more stable means being able to hold a charge better. And so, for instance, losing a hydrogen and becoming negatively charged, you would be able, the one with SP, the one with more S character, is going to hold that charge better. And so we can actually see that in the pKa's of these. So we have ethane, which is our 2-carbon alkane, that has a pKa of 50. Ethene, so this is, remember, SP3. This is SP2. We're now down to pKa of 44, and this is SP right here. Now we drop to a pKa of 25, and so that has to do with that S character being able to hold more charge onto it. All right, and so now the last thing I wanted to touch on in this video was Lewis acids and bases. And so I'm going to go through this kind of quickly because we'll sort of talk about it and pick up on it in terms of context in later videos when we start talking about nucleophiles and electrophiles. But for now, just know that a Lewis acid is what is called an electrophile, and a Lewis base is what's called a nucleophile. And so those words come from this, so this phile right here, which is Greek for love. So they have this phile here. So an electrophile is something that loves electrons, and a nucleophile is something that loves nuclei. And what that means is that the nucleophile, which is always going to have this lone pair of electrons here, this lone pair wants to find a nucleus, and so it's a nucleophile because it's always searching for a nucleus. Where an electrophile, like what I have here, is this carbon, which is going to have a partial positive because there is a dipole moment pointing that way. And so because it has that partial positive, it wants electrons. It wants negatively charged electrons. And so that's where that electrophile comes from. It loves electrons. And so another thing you'll often hear these referred to as is electron pair acceptor and electron pair donor. So like I said, the Lewis base, the nucleophile, is always going to have this electron pair right here, and it wants to donate that. So it wants to go towards a nucleus and sort of donate its electron pair to that nucleus. And so that's what Lewis acids and Lewis bases are. So let's look at a few examples here. So we have our Lewis acids. This you might think, well, didn't you say that like the methane is not acidic? But this, we're not talking about sort of losing this hydrogen here. We're actually talking about this right here coming and attacking the carbon right there, and then this leaving like that. And so we have this as our leaving group here, and so we now have this this methanol that has attached to this right here. And what you'll notice, and I'm not going to go into it too much here because we'll talk about it more in later videos when we get to like SN1 and SN2 reactions, is you'll notice that the hydrogens going from the reactants to this product have sort of inverted, sort of moved over into this direction. And so that is a hallmark of SN2 reactions. But like I said, I'm not going to get into that right now. But just know that this is acting as the Lewis acid because this partial positive carbon here, because there is a dipole moment going in that direction. And in fact, well, I'm not going to get into it. That's for the later videos. But anyway, this is acting as the Lewis acid because it's acting as the electron pair acceptor, and this is the Lewis base because it's donating this electron pair right here, and so it wants to go after the carbon nucleus in this structure right here. All right, another example, and this is sort of a perennial favorite when talking about Lewis acids and bases, is this trifluoro boron here. And so this the boron is kind of an interesting atom because this is going to have like an empty p orbital here, and so these electrons here want to go into that p orbital, and so we will end up with a structure that looks like this. So the nitrogen has donated its electron pair, and the sort of trigonal planar geometry of these fluorines have now sort of been pushed over like this, and so now it's a tetrahedral structure on the boron there. If we're just looking at the boron, obviously this whole molecule is not tetrahedral, but just looking at the boron, the geometry on the boron is tetrahedral now. So another place that these things pop up a lot is in coordination chemistry. And so I haven't gotten to it as of recording this video, but I will be talking quite a bit about coordination chemistry in my inorganic chemistry playlist at some point. But anyway, we have this aluminum here with a 3 plus charge, and these waters come in and form a coordination complex around it in this octahedral geometry right here. And so again, the aluminum is acting as the Lewis acid, and the waters are acting as the Lewis base. And so it's actually here, this is one way that I think about it, because I think it's these metals acting as Lewis acids that I think people get the most confused with, because there isn't any kind of hydrogen anything going on with them. So the way I think about it, so we will have 5, and we'll put H2O here, and then this one I'm going to put explicitly, and so that's on there. And so we have this bond going to this, or this coordination complex going to this aluminum. And so there is, I guess you could say, like a partial positive going on this oxygen. And so the electrons can go onto there, and this releases a hydrogen. And so that's how we can think of these metals as acting sort of like a Bronsted-Lowry acid, because with these waters bound to it, they can sort of release these hydrogens, acting like a Bronsted-Lowry acid. And so, if that helps you to think about the metals like that as acids, then yeah, that's the way that I sort of conceptualize it. Then, of course, we have the canonical Bronsted-Lowry acid and base here, where the hydrogen ion is an electrophile. So it's an electrophile, and this is a nucleophile. And so the Bronsted-Lowry acids and bases are actually a specific or particular case of Lewis acids and bases, where Lewis acids and bases are much more general than Bronsted-Lowry. But the Bronsted-Lowry acid, the H plus ion, is in fact a Lewis acid as well. And the sort of canonical Bronsted-Lowry base here is in fact a nucleophile, or Lewis base as well. So this is also a Lewis base. I'll capitalize the L on here. And this is a Lewis acid. And so, like I said, the Bronsted-Lowry acids and bases are a specific case of Lewis acids and bases, but the Lewis acids and bases are much more general. When it comes to the Lewis acids and bases, though, in organic chemistry, we use these terms right here quite often, especially nucleophile. Nucleophile is a term that gets tossed around a lot in organic chemistry. But anyway, that was everything I wanted to talk about on this video. I think, like I said, the two big take-home messages, and I'll even write them down here. So the first one is that acids and bases are inverse of each. Oops, that should be each other. So that's kind of one of the big take-home message. If your acid gets stronger, then your conjugate base gets weaker, and if your base gets stronger, your conjugate acid gets weaker, and so vice versa. And the other one is that it is context dependent. So if you put something that's an acid into something that's an even stronger acid, then your acid is now going to act as a base. And I guess maybe a third one that I'll add here is that a molecule can have multiple, so acid, base, sites. And so I think these are probably the three main take-home messages for this video, that acid strength and base strength are sort of inverse of each other, that the strength of an acid, or whether something is even acting as an acid or acting as a base, is context dependent, and a molecule can have multiple acid and base sites. And so we saw that, for instance, with our acetic acid here, where we could have this as an acid site, and if we have a hydrogen bound to this, then this is also an acid site, and they have their own pKa's. So the this one up here was a pKa of -5, and this one is a pKa of 4.74. And so, yeah, they could, the same molecule can have multiple acid and base sites on it. One last note too is when we look at these charts here, like I said, they're kind of a dime a dozen if you just do a Google image search. What you'll notice is that the numbers on them are not always exactly the same, especially when we get to these edge cases like this right here or this right here. And that's because when you start getting to those cases where you're taking the negative logarithm of like a k a ka that's, on the order of like 10 to the well, it wouldn't be negative, so it'd be like 10 to the 7, or 10 to the 8, or even higher, sometimes like up to 10 to the 15. The number of products, and we saw this in the previous video, that you start asymptoting towards 100% products. So if this is the 100% products right here, you start asymptoting towards it, and so it starts getting harder to measure sort of these edge cases. And you can even see on this right here, they have 50, 36, and then when they finally get down to here, they start having more and more significant figures on these, and then as we go back this way, we start losing significant figures. And so if you see things that have slightly different numbers on them, don't be too worried about that. Just know sort of the ballpark, because I've seen HCl at -6 before as well. And so as long as like within that ballpark, then we're doing good. But you'll get nice and precise ones here when you are in sort of the range of pH in water. And that is because of that thing I was talking about earlier, about how the hydroxide in water is always going to be your strongest base. And so our best measurements are going to be between pKa of 0 and pKa of 14. So when you start getting outside that, then you start losing a little bit of accuracy on that. But anyway, I'm kind of rambling. I hope you found this video helpful, and I will see you in the next one.